So what I'm going to draw in the middle of my screen here is a complex number plane. The horizontal axis corresponds to real numbers, and the vertical axis corresponds to imaginary numbers. The right-hand side of the graph is positive, so quadrant 1, I guess, is positive real part, positive imaginary part. Quadrant 2 is negative real part, positive imaginary part. Quadrant 3 is negative for both. Quadrant 4 is positive real, negative imaginary. So complex numbers come in two different forms, actually three, but two of them are literally the exact same thing expressed in just slightly different format. So over here on the left-hand side, we're going to start with the rectangular form of a complex number. Okay. So let's say that I have a complex number A, and I'm going to put a bar over it to let you know that I'm dealing with a complex number. In textbooks and things like that, you might usually see this just depicted as a boldface character, but because I can't write in bold, I'm choosing this notation. And I'm going to say that complex number A is equal to lowercase a plus j b. Okay. So A here represents the real part of complex number A, and B here represents the imaginary part of complex number A. So on our complex plane, we would go out A units in the real direction, up B units in the imaginary direction, and would wind up with a complex number A, like so. So when you guys had your probably pre-calculus class, or when you dealt with imaginary numbers in your high school math classes, what was the imaginary operator? Say it louder. I. Anybody have any idea why we don't use that in electrical engineering? Because I is current, exactly. So J right here is the imaginary operator that is equal to the square root of -1. Has the exact same value as I you're used to in all of your math classes and stuff like that. But in electrical engineering, we can't use I because it's used for current so often. Okay. So just wanted to be clear about that. Okay. So we have this complex number plotted on our complex plane. And now we're going to get into the two other forms. So the first one that we're going to start with is the exponential form. And then the next one that we're going to talk about is the polar form. And the exponential form and the polar form of a complex number literally contain the exact same information. It's just expressed slightly different. Okay. So in exponential form, our complex number A is going to be given by the magnitude of A, so the length of that vector, e to the j theta A. So the length of this vector is the magnitude of A. And the angle formed between the complex number and the positive real axis is the angle theta A. our polar form representation of this same complex number, sorry, is simply the magnitude of A angle operator theta A. So literally the exact same pieces of information, magnitude and angle, but expressed in a slightly different form. Okay. Your calculator can interpret this style of complex number and this style of complex number. The exponential form confuses the hell out of it. So anytime you're given an exponential form complex number and you want to use your calculator, simply convert it over into a polar form complex number by simply keeping the magnitude, keeping the phase angle, and throwing everything else away. Okay. All right, so let's talk about how we can go back and forth between these different formulations. All right. So if we want to convert a rectangular form to polar, what would the magnitude of our complex number A be? Anybody have any thoughts? Exactly right. Just good old Pythagorean theorem because it's a right triangle. So the magnitude of a complex number is always the real part squared plus the imaginary part squared, which for this particular complex number is going to be the square root of a squared plus b squared. 100% correct. What about our phase, excuse me, I don't want to call it a phase angle yet. Our angle theta A. Lots of different trig identities that we could use here. The one that I prefer is the arc tangent of the imaginary part over the real part. Which is literally just the arc tangent of B over A. I am going to put an asterisk here to remind myself to talk about the limitations of this approach in a moment. And it's a limitation of your calculator, not so much a limitation of the math. Okay. So now let's talk about going the other way around. If we want to convert a polar form complex number into a rectangular form complex number, anybody have any thoughts on how we might do that? Basic trig, right? So if we want the real part of complex number A, this is going to be the magnitude of A cosine angle theta A, or we could say A is simply the magnitude of A cosine theta A. And similarly, the imaginary part of complex number A is the magnitude of A sine theta A, or B is equal to the magnitude of A sine theta A. So we can now go back and forth between the different forms, okay? And yeah, all right. So now let's talk about where this stuff can potentially fall apart, okay? So I'm going to draw here another complex plane. This is my real axis. This is my imaginary axis. And I'm going to have a complex number that is -3 units in the real direction, +3 units in the imaginary direction. And let's call this complex number X. So in rectangular form, we could say that x is simply equal to 3 plus, sorry, negative 3 plus J3. Anybody have a problem with that? In polar form, our magnitude of x is going to be the square root of negative 3 squared plus positive 3 squared is going to be, if I'm not mistaken, 3 square root of 2, but I'm going to throw it in my calculator just to make sure I'm right. Yeah. And our phase, excuse me, our angle, theta A, would be given as the inverse tangent of our real, imaginary part, which is positive 3, over our real part, which is negative 3. According to my calculator, is negative 45 degrees. Does anybody see what the problem is? You're shaking your head as if you see what the problem is, so tell me what the problem is. Exactly right. So this is a limitation of the calculator, okay? The inverse tangent or arctangent operation will always return an angle that is in the first quadrant or the fourth quadrant. And we can see very easily that our angle is supposed to be in the second quadrant. So effectively, the angle that we got is 180 degrees off of what it is supposed to be, okay? So in this particular case, we would simply need to add 180 degrees because we can see that that'll shift it to the correct quadrant, okay? Now, that is the problem of doing this by hand. Now, your calculator can convert between different forms of complex numbers. And if you do the conversion in your calculator, it will actually do it correctly, and you won't need to bother with learning when to add or subtract 180 degrees. So I'm well aware that the overwhelming majority of you do not know how to use your calculators to do complex numbers yet. So I'm going to spend the next couple of minutes going around answering questions, okay? So for the TI folks, all right, so everybody with a Casio can space out for the next 3 minutes or so. But for the TI folks, your calculator can just do it without having to change the mode or anything like that. So if I type in negative 3 plus 3, and then I press the pi button 3 times, that gives me the imaginary operator I. Then I press second pi, and that brings up the complex menu. And I can scroll down. So this is where I find my angle operator. If I want to enter a number in polar form, I can make it return the angle only of a complex number, give me the magnitude of a complex number. Number 4 converts from rectangular form into polar form. Number 5 converts from polar form to rectangular form. Number 6 is the complex conjugate operation, which we're going to talk about momentarily. Number 7 returns the real part of the complex number. 8 returns the imaginary part of the complex number, and then those are all the different things. So all of your complex number operation stuff is buried in this little pi key right here. That's how you get your operator, and then if you press second, it brings you to the complex menu. So I'm going to scroll down to option 4, press enter, and I get 4.2426, which is 3 times the square root of 2, angle positive 135 degrees, which is exactly what it looks like we should be getting, okay? So for the TI folks, that's how you do complex number conversion from rectangular into polar. And obviously that same menu helps you do from polar into rectangular. Now I have to dig out my Casio 115. All right, so Casio 115 owners, are there any? Since I convinced most of you to buy a 991, did anybody get one of these instead? All right. You did? All right, I'll deal with you individually in a moment. Okay. Can I borrow your 991 for just a moment? All right. So for the 991 calculator, the first thing that you need to do is press the menu key and put your device in complex mode, which I'm trying to remember exactly where that is. Second, okay. So the second option puts your calculator in complex mode. I'm going to type -3 plus 3, and then I press the engineering button, ENG, to give me the imaginary operator. Pressing Shift engineering button gives me the angle operator. So that engineering button is where you get your rectangular form complex numbers and your polar form complex numbers from, okay? Now I'm going to press the option button here in the top left. And this is my different options that I have for manipulating complex numbers with a Casio 991. So the argument thing, number 1, returns the angle. Number 2 is the complex conjugate operation, which we have not yet discussed. Number 3 is the real part. Number 4 returns the imaginary part. Pressing down brings you to the second page of the menu. Number 1 converts into polar form complex numbers. Number 2 converts into rectangular form complex numbers. So we would press option down 1 equals, and we get 3 square root of 2, angle 135 degrees. Thomas, you said you know how to do it? Okay. So for you, you don't have the option button, then you hit shift 2. That's what it's up. The engineering button is where you get I and shift engineering button around like right now it's set. So you can change it if you want to do so if you want the result default into a Yep. All right. Anybody have any questions about the very limited operation I've asked you to do here in converting from rectangular to polar with your calculator? So we're all on the same page. All right. Okay, so now we're going to talk about the complex conjugate operation. So I'm going to erase this example just because I wanted to show you what the limitation was. So the complex conjugate operation is depicted by putting an asterisk next to your complex number. Okay, so this means something very specific. When you're dealing with complex numbers, this does not remotely mean multiplication or anything like that. Okay, so I want to be very, very clear. So what the complex conjugate operation does is it flips your complex number across the horizontal axis of symmetry. So this complex number would be a conjugate, okay? So it has a real part of A an imaginary part of negative B and forms an angle, negative theta A with the positive horizontal axis. So in rectangular form, the complex conjugate operation simply means we change the sign on the imaginary part. So if complex number A is A plus JB, A conjugate is A minus JB. That's it, okay? In polar form, this operation is simply changing the sign on the angle. So complex number A conjugate is going to be the magnitude of A with an angle of negative theta A, okay? Your calculators can do this conjugate operation for you. It's buried in that complex menu. For the TI folks, again, that was pressing second and pi. For the Casio 991 folks, that is found by being in complex mode and pressing the options button, okay? And for Thomas, who's the only person that's using a 115, while in complex mode, pressed Shift 2 to bring up the complex menu, and that's where you'll have access to the conjugate operation. All right, so now we have, I think, clarified what complex numbers are. It's just a number that contains both a real and an imaginary part. We can go between the different forms and all that kind of stuff. Now let's talk about what the mathematical operations detail. And I want to be clear about this. I'm not actually expecting you guys to have to do this by hand. Your calculators are there for a reason. They're very, very powerful. That being said, there are going to be times when I am deriving things or explaining things where understanding how the operations work will be helpful for you to understand what the hell I'm talking about. So that's why I'm spending the time to do this. Okay? So let's start with the addition operation. Okay. So let's say that I have a rectangular form complex number that is A is equal to A plus JB. A complex number B that is equal to C plus JD. And I want to know what A plus B is. So I'm simply going to have A plus JB plus C plus JD. And I add these like vectors because that's exactly what they are. So the real numbers are vectors in the real number direction. The bits with a J are vectors in the imaginary direction. And so this is just like me adding the X components together and the Y components together to get the resultant. So this is going to look like A plus C plus J B plus D. So that is addition with rectangular form complex numbers. You can't easily do addition with polar form complex numbers. So I would argue that if you're going to do it by hand, always do it in rectangular form. Now we'll deal with subtraction. So if we have those same complex numbers, A is equal to A plus JB, and B is equal to C plus JD, the mathematical operation A minus B is going to be A plus JB minus C plus JD, which is going to look like A minus C plus J B minus D. Pretty much the exact same thing as the addition operation, except now we have negative signs involved. Nothing particularly difficult. And once again, your life will be easier if when doing this by hand, you are using rectangular form complex numbers. Now let's talk about multiplication. So if A is equal to A plus JB, B is equal to B plus, excuse me, C plus JD, then multiplying A and B together is going to look like this. Okay, so I want to point out something here. I'm not going to use this because I am technically dealing with two-dimensional vectors and I don't want you to think I'm asking you to do a cross product operation. I'm not going to do this because I don't want you to think I'm asking you to do a dot product operation. I'm not going to do this because I don't want you to think I'm asking you to do a complex conjugate operation. So when I'm multiplying them together, I just put them next to each other and call it a damn day. That's the only way that I can safely not confuse you with some other potential operation that you might try to carry out, okay? Anytime you see the asterisk sign, you are taking the complex conjugate. Cross product for complex numbers does not exist. Dot product for complex numbers does not exist. I just want to be very, very clear about that because you guys know enough math to now be dangerous, okay? So the multiplication of complex numbers is just one number next to another number implies that multiplication is occurring. All right. So this is going to look like A plus JB times C plus JD. And we FOIL this stuff out just like middle school algebra, okay? So we're going to have A times C plus JAD plus JBC plus J squared BD. Now, what is J squared? Exactly right. So J squared is the square root of -1 squared is -1. So this means we will have AC minus BD as the real part of our resultant, plus J AD plus BC as the imaginary part of our resultant. Okay. So that's what multiplication looks like with rectangular form complex numbers. Not wildly difficult by any stretch of the imagination, but it can be a little tedious. This is where using a different form can make things slightly easier. So if I had A represented as a exponential form complex number and B represented as an exponential form complex number, multiplying A by B would be simply the magnitude of A, e to the j theta A, times the magnitude of B, e to the j theta B, which looks like the magnitude of A multiplied by the magnitude of B times e to the j theta A plus theta B. So multiplication with exponential form complex numbers is just multiply the magnitudes, add the angles. Pretty trivial. And it's obviously the exact same thing in polar form complex numbers because polar form complex numbers is really just a shorthand notation for exponential form complex numbers. Okay. So just to show you exactly what that would look like, if A was A angle theta A, B were the magnitude of B angle theta B, then A times B would be the magnitude of A, magnitude of B, angle theta A plus theta B. Same result, just in a slightly different. All right. Now, division. So this is going to be a little bit of a pain here in the rectangular form. So complex number A divided by complex number B, I'm going to give myself some space here, and you'll see why in a moment, is going to look like A plus JB divided by C plus JD, excuse me. Now, my expectation is that I should be able to get a rectangular form complex number out of this. And right now I have a ratio of rectangular form complex numbers, which is not the same thing, okay? So how I am going to rectify this situation is I'm actually going to multiply by B conjugate over B conjugate. So this is going to be C minus JD over C minus JD. Foiling this out is going to give me AC minus J AD plus J BC minus J squared BD all over C squared minus JCD plus JCD minus J squared D squared. So we know that this minus J squared here looks like positive 1. This minus J squared here looks like positive 1. Minus JCD plus JCD cancels each other out. And so what we wind up having here is AC minus BD all over C squared plus D squared plus J BC minus AD over C squared plus D squared. So a bit of a pain in the ass. In exponential form, things become much easier. So complex number A over complex number B is just going to be the magnitude of A e to the j theta A over the magnitude of B e to the j theta B, which just becomes the magnitude of A divided by the magnitude of B e to the j theta A minus theta B. So we divide the magnitudes, subtract the angle. Yes. Yes, thank you. Yeah, AC plus BD, yes. And then BC minus JAD, yeah. And then once again, polar form is the exact same result as exponential form. All right. These are all the different operations that I expect you to know how to do using your calculator, okay? So one thing that I do want to point out, your calculator does not care whether you put your complex numbers in polar form or rectangular form or some combination thereof. You can do addition, subtraction, multiplication, and division. Your calculator will handle literally all of that in mixed things, okay? So your calculator is much smarter than you, much smarter than me as well, okay? Not throwing any shade here or whatever. Learning how to manipulate complex numbers is going to be a huge part of what we're going to be doing here in the future. I will say very emphatically that you should learn to and get in the practice of storing numbers in your calculator's memory sooner rather than later, because of the ludicrous amount of bookkeeping that goes along with doing complex math, okay? It is far too easy to make simple mistakes when you're dealing with real parts, imaginary parts, magnitudes, and angles. All of that information buried inside of stuff. Storing numbers in your calculator's memory will make your life infinitely easier, okay? All right, so at this point, you should be able to do what's up, Ryder? Wonderful question. So, no, very, very good question, for which I am going to spend a significant amount of time on Friday explaining to you why it's applicable, okay? So now we're going to talk about sinusoids. I'll give you a very short answer now. Using complex numbers will allow us to transform calculus-based relationships into algebra-based relationships, which will be much, much easier to deal with. We will see that firsthand with an example problem that I'm going to work on Friday. I'm going to work it 3 different ways, and using complex numbers makes it 2 lines of math. Other methods make it like 6 pages. So, all right. So, sinusoidal signals. All right. So the next third of our class, the last module, if you will, is all about what's called steady state sinusoidal analysis, okay? So here in the United States and practically every other industrialized nation in the world, electricity, power, et cetera, are distributed using sinusoidal signals. So the voltage that comes out of these plugs or receptacles in our walls is not a DC quantity, it's actually an AC quantity. In that receptacle, it's generating a time varying voltage that is going to be something close to 120 square root of 2 cosine 120 pi t plus some particular phase angle. Dealing with that amount of information is going to be wildly annoying, but we do need to understand what's going on there, okay? So we're going to start by looking at the characteristics of sinusoids. So you're going to have to bear with my terrible drawing skills here for today, and then we'll move along from it as soon as we possibly can. So here, I'm going to plot, let's call it an arbitrary voltage waveform as a function of time. Okay. So this is my shoddy attempt at a sinusoid, okay? So mathematically, this function v of t could be described as Vm cosine omega t plus some phase angle phi. And technically, we could also describe it as Vm sine omega t plus some arbitrary phase angle theta. And there is a relationship between phi and theta that we'll discuss briefly, okay? So I want to talk about the constituent parts of these representations. So the first thing we're going to focus on is Vm. Okay. So Vm is the magnitude or amplitude of our sinusoidal function v of t. So this represents the distance between the peak value and the horizontal axis. It does not particularly matter whether you're talking about a positive peak or a negative peak. Okay. Omega is the angular frequency of our sinusoidal signal. Okay. So it is measured in radians per seconds. Always, always, always. Angular frequency is measured in radians per second. Okay. Now, right now, this might not mean anything to you, so I want to talk our way through it. Okay. So the amount of time that's measured between the bottom peak and the next bottom peak, or the positive peak and the next positive peak, or the zero crossing where the signal is increasing and the next zero crossing where the signal is increasing, is the period. So effectively it represents the periodicity, or how often this thing repeats. Okay. Linear frequency f, so this is all an aside thing here. So t is the period of the waveform, which represents the duration in time of one cycle. Okay. Our linear frequency f so linear frequency of the waveform which represents how many cycles occur in 1 second. So this unit is hertz, which literally means cycles per second. And there is a relationship, F is equal to 1 over t. So period is the number of seconds per cycle. Linear frequency is the number of cycles per second. So they're literally just the inverse of each other. Okay. Angular frequency is simply 2 pi times the linear frequency, because each cycle corresponds to a change in angle of exactly 2 pi radians. Okay. Or 2 pi over our period. So if we are given a graph of a sinusoid, you now know how to get the angular frequency just by looking at it. Okay. So we've taken care of this bit, this bit, this bit, this bit. So now we have our phase angle things to deal with. Okay. Yes, omega is equal to 2 pi f. is equal to 2 pi over capital T, the period. All right. So now we get to the thing you're probably the least familiar with, our phase angle phi. So phi is the phase angle of our waveform V of t, and it determines the value of V of t at t is equal to 0. So I'm going to scroll up here really quickly. So I said a moment ago that we could represent this as either a cosine function or a sine function, right? So for a cosine function with a phase angle of 0, we would expect our function to be at its maximum value at t is equal to 0. But instead, we see our maximum value at some later point in time, right? Some positive value of lowercase t. So this particular waveform is shifted some number of time units to the right. If we were looking at this from the perspective of a cosine, or excuse me, a sine function, we would expect it to have a value of 0 at t is equal to 0 if the phase angle were 0. It would have a value of 0 and be increasing, okay? Instead, it is 0 and increasing at some point earlier than t is equal to 0. So from a cosine perspective, this looks like a shift to the right. From a sine perspective, this looks like a time shift to the left. And those are quantified, that amount of time shift is quantified by what that phase angle is, okay? So it's literally just telling us by how much we have manipulated this guy throughout a portion of its cycle to make the graph look like this, okay? So changing the phase angle shifts the waveform along the time axis without changing the amplitude or the frequency, linear or angular, of the device, or of the waveform, okay? So phi only corresponds to how much the entire waveform is shifted left or right. It has nothing to do with its peak. It has nothing to do with how often it oscillates. It's only moving it back and forth in the time direction, okay? So positive phase angles, or phi greater than 0, cause shifts to the left, okay? So from the perspective of the sine function, we would have a positive phase angle theta. That seems counterintuitive to a lot of you, but effectively what it means is that we are hitting the expected value earlier than t is equal to 0, okay? So it causes shifts to the left by delta t is equal to phi over omega. Negative phase angles, where phi is less than 0, cause shifts to the right by that same delta t is equal to phi over omega. So effectively, a positive phase angle means that we are advancing the waveform, moving it to the left to an earlier point in time. Negative phase angles mean that we are delaying the waveform, shifting it to the right at a later point in time, okay? It seems counterintuitive, but it's all based on the fact that we read graphs from left to right, where left of 0 means that we are at an earlier point in time, and to the right of 0 means that we are at a later point in time. All right, so I have another note here. While omega is always measured in radians per second, phi, our phase angle, is traditionally measured in degrees. This isn't actually going to be a thing for us to worry about for about 2 weeks. And then for a very specific type of problem, we have to pay attention. And then if we're not dealing with that very specific type of problem, we no longer give a shit. So. All right. So now I'm going to introduce several trig identities that we are going to wind up using throughout the remainder of this class. Okay. So trig identity number 1 says that cosine of omega t is equal to sine of omega t plus 90 degrees. So effectively, if we were to shift a sine function to the left by 90 degrees, we would wind up with a cosine function. We can then say that sine omega t is equal to cosine omega t minus 90 degrees. So we can now go back and forth between sine and cosine functions. All right. Negative cosine omega t is equal to cosine of omega t plus or minus 180 degrees. So effectively, a negative sign indicates that we have shifted it by half a cycle in either direction. Now we'll do the same thing for sine functions. All right. These are all fairly straightforward and just deal with shifting back and forth. Now we are going to look at some other identities. So let's say sine of some angle alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta, and cosine alpha minus beta is equal to cosine alpha cosine beta plus sine alpha, sine beta. These four trig identities right here effectively represent what we are going to be doing when we are analyzing circuits in the time domain, which we are not going to do very much of, and it'll be very obvious why once we do it once as to why it's a huge pain in the ass, okay? But so these four trig identities right here are what we're going to spend a significant amount of time on Friday utilizing. Anyway, we have a couple of other trig identities that we're going to wind up using. Cosine alpha times cosine beta is going to be 1/2 cosine alpha minus beta plus 1/2 cosine alpha plus beta. There are technically other trig identities for, cosine times sine, sine times cosine, sine times sine. But since we know how to convert anything to a cosine function, we can just know this single one and use it for every possible combination. So I never bothered to learn the other three. Okay. This one is going to show up multiple times in about a week and a half when we start dealing with power-based relationships, when we're multiplying sinusoidal voltage functions times sinusoidal current functions to figure out how the power behaves. It's also going to be a sinusoidal function following this rule. And then our last trig identity is what's called Euler's identity. And Euler's identity says that cosine of omega t plus j sine of omega t is equal to e to the j omega t. So effectively, Euler's identity relates sinusoidal functions to exponential functions. And this is the key thing that allows us to analyze circuits in what we're going to call the frequency domain, which is what we're going to start doing at the end of class on Friday. Okay. So I have one last thing that I want to talk about here briefly, and that is comparing sinusoids and the concept of leading and lagging. So to compare sinusoids, three criteria must be met. Number one, all functions or waveforms must be expressed exclusively as sine waves or cosine waves. So let's say that I have some voltage VA of t, and it is 8 cosine 7t plus 10 degrees volts. Some voltage VB of t that was 4 sine 7t minus 30 degrees volts. In order for me to compare these, I would have to convert the cosine function into a sine function or convert the sine function into a cosine function. For reasons which will be explained on Friday, we are going to use the cosine function as our basis or our reference. Always, always, always. In electrical engineering, it makes sense to use the cosine function for reasons that I will explain on Friday, okay? So how do we convert this sine function into a cosine function? Well, if we look at our trig identities, so let's scroll back here. Cosine is equal to sine plus 90 degrees. So we simply add 90 degrees to our sine function and we get a cosine function. So this would look like 4 cosine 7t plus 60 degrees. Yes. So adding or subtracting 90 degrees absolutely matters. Adding or subtracting 180 does not, okay? So adding or subtracting 90 degrees means we're shifting it by a quarter cycle, not a half cycle. So that's why it's important that we do it the correct way there. Our next criterion is that all functions or waveforms must be expressed with positive amplitudes. So let's say that we had a third signal that we were trying to compare. Let's call it VC of t. And it was -6 cosine 7t plus 105 degrees volts. We would need to convert that into +6 cosine 7t plus something else in order to make that comparison with the other signals. So this will look like +6 cosine 7t, and I am going to subtract 180 degrees here. The reason why I am subtracting, it literally does not matter, just to be very clear, but the reason why I am subtracting is because if I subtract 180 degrees from 105 degrees, I'm going to get a number that falls between -180 and +180. So effectively, the angle is going to have the smallest possible numerical value. Just a point of how I like to do it, not anything that you have to follow through with, unless, of course, your homework problem specifically says, give me the answer with the smallest possible angle, which does occur at times, okay? So 105 minus 180 is, I believe, -75 degrees. If my mental math is incorrect, please tell me so. Our third criterion is that all functions or waveforms must have the same frequency. There is no trig identity to fix this. Okay. They either have the same frequency and you can make a comparison, or they do not and you cannot. Okay. So there's no way to make something with an angular frequency of 7 radians per second look like an angular frequency of anything other than 7 radians per second. All right, so now we're going to talk about the concept of leading and lagging. So I am once again going to try to draw something for you guys, and I'm going to pre-apologize with how absolutely shitty it looks. Let's see, 8, 4, and 6. So here, I'm going to have my voltage as a function of time, And then on this graph, or excuse me, on the horizontal axis, I'm going to put omega t for now, just because it's going to help me figure out how these things are shifted in comparison to each other. Okay. So this is going to be 90, 180, 270, 360, and on and on and on. All right. So VA has a phase angle of positive 10 degrees. And that's in blue, and it has a magnitude of 8. So that's going to be something very slightly shifted to the left because the phase angle is small and positive. Sorry, I'm thinking about just going onto Desmos or something like that and just doing it graphically on the computer, but I've already started, so I guess I'll leave it at this. So the blue curve is VA of t. The red curve here is going to be VB of t. So we have a cosine with a phase angle of positive 60 degrees. And its magnitude is 3. Sorry, its magnitude is 4, so it should be 1 smaller than that. My apologies. This is looking shittier and shittier the longer I try to do it. Something like that. I think I've messed up somewhere, but we'll just have to deal with it for now. And let's see, purple, we have a phase angle of negative 75 degrees. So that's going to be a shift to the right. Something like this, okay? Okay. Sorry, my watch is freaking out here. So we consider a sinusoidal signal to be leading another sinusoidal signal if it hits its peak value earlier in time. So in this case, we could say that VB, our red curve, is leading VA and leading VC because its peak value right here happens at an earlier point in time than the peak value of VB or the peak value of VA or the peak value of VC. So VB is leading VA and VC. by some specific amount, which is hard to determine from this particular representation. Similarly, we can say that a signal is lagging another signal if its peak value occurs later in time. So for example, VC is lagging VA and VB because its peak value occurs later in time, okay? That's how we read leading and lagging on a time domain graph like this. I find it difficult and confusing, okay? I prefer to use what's called a phase diagram to make these assessments, okay? So what a phase diagram is a snapshot in time of our sinusoidal waveform. Typically that snapshot in time is taken at t is equal to 0, so that we're really just left with a magnitude and a phase angle that we have to worry about because the cosine of 0 is just 1, okay? So this is our time domain graph, which again, I feel is a huge pain in the ass to try to figure out how to read. Our phase diagram is going to look something like this. So this corresponds with 0 degrees, 90 degrees, plus or minus 180 degrees, and negative 90 degrees. Our signal VA has a phase angle of positive 10 degrees and a length of 8. So this would be a representation of VA of t, where this angle is positive 10 degrees. VB has a length of 4 and an angle of 60 degrees. So this would be a representation of VB. And VC has a magnitude of 6 and a phase angle of negative 75. So something like this. Okay. So this is a phase diagram, okay? We can do our leading and lagging comparisons here as well. So effectively, if I wanted to know by how much does VA lag VB, I would start by measuring from VB, and I'll measure in a in a clockwise direction, okay? So the difference between these angles is 50 degrees. So we could say that VA lags VB by 50 degrees. If we wanted to know by how much does VB lead VC, we would start measuring from VC and measure all the way around until we hit VB, which in this case looks like 75 plus 60 or 135 degrees, okay? So sorry, I'm gonna write this down. Leading is always measured counterclockwise because we're looking for a more positive angle. Lagging is always measured clockwise from our reference, okay? So what I'm gonna do right now, we got a couple of minutes here. I'm gonna pull up WebWork and we're gonna look at a homework problem from homework set 19 because I want to point you guys to a small problem that WebWork has. So the way that I have described this is perfect because, as we all know, I am perfect. It's a huge joke. But if you use the thing that I have just showed you, WebWork will sometimes have a minor panic attack. Okay. So let me see which problem it is if I can remember. That's not it. That's using trig identity stuff. That's going to be a pain in the butt to do. Let's go back to problem 1. Okay. So leading and lagging here. So we have a fixed value of V1 and we have 3 different values of I1. Okay, so let's work part A here for my random number seed. So V1 is 194 with an angle of -69 degrees. So I'm just going to come down here, make myself a new plot. I already forgot what I said the value was, so -69 degrees. So I'm going to do V1 in blue, -69 degrees is going to be something like this. So here is V1. Now I'm going to do the current for part A. Positive 66 degrees is the phase angle. Notice here, V1 is expressed as a cosine function. I1 is expressed as a cosine function, so I don't have to do any manipulation of my sinusoids. For part B, I1 is expressed as a sine, so I need to convert it into a cosine. For part C, I1 is expressed as a cosine with a negative amplitude, so I need to convert it to a positive amplitude in order to do this, okay? So anyway, positive 66 degrees for I1. All right, what we are trying to find is the angle by which I1 lags V1. So V1 in this case is our reference, okay? So that's where we start measuring from. Because we are measuring lagging, we need to be going in a clockwise direction. So we are going to start from here and go all the way around until we hit I1. So there is 21 degrees between this angle and this vertical thing. Here's 90, here's 90. And sorry, this was, I think, supposed to be 66, not 60. So that's going to be 24 degrees. So this is going to look like 21 plus 180 plus 24. So let's see, that's 201, 225 degrees. Seems fairly straightforward, right? Now let's see what happens if I put this number in to WebWork. $225. Submit answer. It says it's wrong. I know emphatically that I am right because I can do that little amount of math in my head, I think with a reasonable degree of accuracy, okay? So here's what the problem is. WebWork doesn't know that 0 degrees and 360 degrees and negative 360 degrees and 720 degrees and negative 720 degrees, et cetera, are all actually the same angle. WebWork isn't smart enough to figure that out. So what I'm going to do here is I am going to subtract 360 degrees, move this thing around 1 revolution. It's literally this exact same angle, and I'll be damned, the answer is correct. So if you're doing this correctly, or if you believe you're doing it correctly, and WebWork tells you that you've got it wrong, add 360 degrees, see if that solves the problem, subtract 360 degrees, see if that solves the problem. One of those three permutations will be correct. And it's all because WebWork doesn't understand the equivalence between the angles. So there's a very distinct possibility that you're doing everything correctly, but a limitation of WebWork's ability to interpret things based on how this was programmed is the reason why you're getting the answer incorrect, or these types of problems. I just want to make you all aware of that. I'm not bullshitting you. I did tell you how to do it correctly. It's WebWork that's a little sketchy for this type of problem. All right, that is enough ranting out of me for today. So you do have 23-ish minutes left, which should be plenty of time to knock out that in-class assignment, since the expectation there is that you're literally just learning how to do use your calculator. You don't have to show me a whole hell of a lot of work because you're using your calculator. If you have any questions about how to use your calculator, please let me know and I will help you. All right.